Thank you everyone for tuning in. I'm Manish Shetty, a postdoc at the University of Minnesota and a faculty candidate. And today I'm excited to share my computational work on the electric field assisted modulation of surface thermochemistry. Why do we care about surface thermochemistry? Because surface thermochemistry and reaction kinetics are interlinked. And these are interlinked through something called as a Bronsted-Evans-Poligny type relationships or BP relationships. And as you can see here in the graph on your left, the transition state energies and the reaction dissociation energies are linearly correlated for a whole range of dissociation reactions. And what this helps us is through computationally inexpensive computations, which can look at dissociation energies or compute dissociation energies, we can estimate the reaction kinetics. Therefore, these BP relationships are really crucial in terms of estimating kinetics from thermodynamics. One of the consequences of these BP relationships is the existence of these volcano curves or Sabatier curves, where two or more of such competing linear scaling relationships lead to an volcano type behavior, where certain catalysts such as platinum shown here for formic acid decomposition to CO and H2O ends up being the most reactive or the most optimum catalyst. And one end of the volcano are metals or catalysts which do not activate the key intermediates well. And on the other end, we have catalysts which activate it too well or strongly bind them where almost they start acting like poison. And in general, catalysis design-based approaches are focused on overcoming these rate limitations through material science-based approaches. And in a recent review by Perez Ramirez and Professor Lopez, what they've looked at or tried to review a whole range of approaches, where a whole range of these approaches are looking at material science-based approaches, including single atom, alloys, ligand-based approaches. However, an interesting class of approaches is the looking at external stimulus, such as mechanical stimulus like strain, magnetic or electric fields. And an example of this was a recent work coming from Notre Dame on plasma-enabled catalysis, where they looked at ammonia formation. And as you can see in these graphs, through plasma, they are able to overcome the static optimums and be able to get multi-order rate increases for ammonia formation from nitrogen and hydrogen. What we've been interested in is an alternate strategy looking at oscillations. What do they mean for a hypothetical conversion of A to B in the gas phase, which goes through a surface intermediates A star and B star with a surface reaction barrier EA and the adsorption enthalpies HA and HB? What we are able to show through these simulations is if the catalyst oscillates through two distinct electronic states, in one state where the surface reaction is fast, where A star and B star are both strongly adsorbed, and in the second state where B star and is weakened by decreasing its desorption energy, making it weakly adsorbed, we are able to achieve rate increases which are multi-order magnitude higher than the static optimum. Essentially, we have catalysts flipping between two distinct electronic states. But in general, as I've mentioned, there's changes in binding energies which are required to be able to achieve these rate optimum increases or rate increases. And the main question we ask is, can electric field modulate these binding energy changes, or can they have enough changes in binding energy? Specifically, purpose of this study, we ask three questions: whether the linear scaling relationships, which are shown before, which are periodic trends as we change different catalysts, remain the same under electric field. If not, in a way I've given you the answer, they do not. Can we develop similar linear scaling relationships under electric field? And can we make this field dependent properties predictive? Why do we care, or why is it important? Is because we can take the results of this study and model catalytic behavior for different catalysts and therefore predict the catalytic behavior under dynamics or under oscillations. We use DFT for this study for density functional theory computations, and we use platinum 111 as the model surface. On platinum 111, there are different kinds of sites: ATOP, bridge, and FCC and HCP hollow sites with different coordinations, ATOP having a coordination of 1, bridge having coordination of 2, and FCC and HCP hollow sites having coordination of 3. We implement external field through an external dipole as implemented in the software VASP, Vienna ab initio simulation package. And we look at a whole range of adsorbates, 31 in total, which are atomic and molecular in nature, as well as includes hydrocarbon molecules and fragments, halides, and hydrogenated fragments. with the goal of having a huge database which you can use for predictive behavior. First, before going into these questions, what does electric field do and how does adsorption occur? What is the physics when adsorption occurs? To illustrate this, we look at some adsorbates, N2, NH3, COH, F, and CH. These are molecular in nature, atomic in nature, and as well as surface intermediates. In general, when an adsorbate adsorbs on the catalyst surface, there's a change or an exchange of charge density or exchange of charge. As illustrated for fluorine, which is the most electronegative element, there's a charge transfer from the surface to the atomic fluorine, causing a dipole in the negative z direction. The consequence of this on the adsorption energies is that on positive electric field, fluorine weakens. As regards to the other adsorbates and CH star shown here, what you have is a charge transfer in the opposite direction from the adsorbate to the surface, causing a dipole in the positive direction. Therefore, for most of these adsorbates, there is an opposite effect where on positive electric field, there's a strengthening of the adsorption. And in general, a point to note are these adsorption energy changes are quadratic in nature, but the second order term is given by the molecule polarizability. And what is molecule polarizability? If we were to plot dipole moment in the y-axis and the electric field in the x-axis, the slope of that would give you the molecular polarizability. Therefore, in general, overall, the sensitivity of the adsorbate to the electric field depends on the extent as well as the direction of these charge transfer and the strength of the dipole moments. So we go about asking the first question. Do electric field dependent linear scaling relationships remain the same as periodic trends? To illustrate this, we'll pick a whole range of monovalent adsorbates, NH2, CH3, thiol, and fluorine, and we plot their adsorption energies under electric field with the adsorption energy under electric field for hydroxyl. In general, that we find as these linear scaling relationships hold, and one of the reasons is being the second order corrections, the polarizability values being weak, which I'll illustrate or describe more in detail. But if you look at their slopes and compare them with periodic trends in literature, what we find is these slopes are distinct as compared to periodic trends. The one in purple or dark blue, what you have is these slopes, which are slopes shown in the left, are distinct for periodic trends. And keeping in mind, when I say periodic trends, these are as we change different metals. And this is not just true for these monovalent adsorbates. If you look at other adsorbate pairs as shown in the x-axis, in general, this violet and red bar graphs, you can see that these slopes are distinct in general as distinct. Therefore, under electric field, the scaling slopes are distinct as compared to the ones that we observe for periodic trends. Not just that, these were for adsorption energies. If you look at BP type relationships that we can develop, which connect their activation energies to the reaction energies for a whole range of dissociation reactions, what we find is that these slopes and the intercepts of these BP type relationships under electric field, if you compare them to BP relationships for periodic trends, these are also distinct. So in general, we'll have to develop these strategies or these insights under electric field. We cannot use the field independent properties such as BP relationships to predict catalytic behavior. We'll have to develop these under electric field for the different metals and the different catalysts. Now that we've established these field dependent properties are distinct as compared to periodic trends, the next question is, can we develop similar linear scaling relationships? To illustrate these, I've plotted CHX adsorption energies and NHX adsorption energies with respect to the binding elements C star and N star. And these are typically what are plotted for periodic trends. In general, they are seen from the regression coefficients. You see that these linear trends do not hold as well. And this is because these adsorption energies of the atomic elements are strongly quadratic, which means the polarizability values are large as seen from these curvatures. And even if you look at the slopes, let's say CH3 and NH3 as an example, 3.11 and minus 4.9, and we compare them with periodic trends as seen in the table, they are distinct, which is what we had seen before. But a key takeaway from this slide is that we cannot plot as periodic trends with respect to the binding element. We need to find other ways of doing it. And a key clue is this second order term. If we have atomic elements which are weaker second order corrections, we can potentially develop similar linear scaling relationships. And that's what we find. If we were to plot these CHX and NHX adsorption energies under field with respect to H star adsorption energies, these linear scaling relationships hold as seen from very high regression coefficients. So we have another way of now plotting linear scaling relationships. What we find, please focus on the slopes, which are CHX or any adsorption energy fragment under electric field as compared to H star. Now the next question is, now that we have another way of finding it, plotting it, can we make this field dependent properties predictive, field dependent adsorption energies predictive? And one way to do that, as I had said, is the scaling slopes, which is a slope of the adsorption energy changes with respect to adsorption energies of H star. For a whole range of adsorbates, these scaling slopes are linearly correlated themselves with the surface adsorbate dipole moment. So now, if we have a sense of the surface adsorbate dipole moment and knowing the scaling slopes, we can go back and calculate the field-dependent adsorption energies for a whole range of these adsorbates, with a slope given by the inverse of the zero field dipole moment of hydrogen. And to look at a simplified derivation which follows from the field-dependent adsorption energy changes, in the presence of weak second order corrections, these gamma or the scaling slope simplifies as a slope given by the inverse of the zero field dipole moment of hydrogen. And that's what we find. These slopes are really close. Are there other ways of getting these linear scaling relationships? One other way we thought about plotting was work functions versus a zero field surface adsorbate dipole moment. Why should this hold? Because there's a charge transfer between the adsorbate and the surface. If there's a charge transfer from the surface to the adsorbate, you have a change in the work function. Therefore, and the other way around as well. Therefore, these should be related to these surface adsorbate zero field dipole moment. And that's what we find. In general, there are two distinct slopes of the work function changes with a zero field adsorbate dipole moments. And we find other ways of being able to predict field dependent properties with field independent parameters, or knowing these slopes essentially. And keeping in mind all adsorbates were included in the analysis. In addition, we also dabbled into machine learning by using random forest algorithm as shown in the left, and I won't go into detail on that. However, what I want to point out is that we're using field or very simple parameters, intuitive parameters like unsaturation, which refers to the valence of the adsorbate. Like, for example, CH, CH2, CH3 will have valence of 3 to 1. Coordination of the site. Platinum has four different sites. The top site having coordination of 1, bridge having 2, hollow sites having 3. And simple parameters that account for the composition, carbon, hydrogen, and oxygen content, electronegativity of the adsorbate, and field-dependent properties such as platinum charge and electric field. We are able to reasonably predict these field-dependent adsorption energies as compared to DFT adsorption energies within 0.1 eV. Keeping in mind these errors can be also observed under DFT when we change the different methods. So with machine learning, we're able to reasonably predict this adsorption energies. So as a summary, we develop linear scaling relationships under electric field, which are distinct as compared to periodic trends. We also developed field-dependent linear scaling relationships, and we also developed predictive models, including machine learning tools, to predict field-dependent adsorption energies. So this is the electrochemical fundamentals talk. So I also wanted to point out, I mentioned about an oscillation strategy, and what we have also been able to show is for formic acid decomposition, which goes through a non-Faraday or non-electrochemical route of formation of adsorbed carbon monoxide, which can be desorbed or oxidized to CO2 electrochemically through a use of an external potential. Using this oscillating strategy, where on one end we accumulate enough CO, and on the other end we are able to desorb them off or oxidize them to CO2. If you oscillate fast enough at inherent frequencies which reflect the inherent timescales of the different processes, we are able to overcome the static rate limitations of up to 20 times. In general, this is one evidence or one demonstration of the use of this oscillation and external stimulus to be able to overcome rate limitations. I also encourage you or invite you to check out a recent perspective in ACS catalysis, where we've looked at other ways of implementing external stimulus, including electric field, where we believe we are able to achieve these rate limitations that we talk about of multiple orders of magnitude. With this, I would like to acknowledge my collaborators, both at the University of Minnesota and University of Massachusetts Amherst, and the rest of the Dow and Howard group. my funding agencies, and computational support. I would be happy to take all your questions in my email, Twitter, as well as in our live chat, or you can catch hold of me anytime through my email and through Twitter. With this, thank you for your attention, and I look forward to chatting with you more and taking this conversation forward. Bye-bye.